Good morning, everyone. This is Jim Chastain with EasyPower. And in our Tuesday refresher this week, we're going to talk about the difference between transient motor start and impact motor start in EasyPower. That's something question that comes up frequently, and it actually is significant because one of the features, the impact motor start, is built into the PowerFlow module, which a lot of people have. So I think it's worth discussing and kind of showing the different approach that each of these modules take on motor starting. So welcome all. Thank you for joining us. And as we like to do at the beginning of these sessions, is I appreciate your responding to a poll question that is relatively short and with no obligation. But basically, what concerns you most regarding motor start analysis on the projects that you work? And again, we have these questions come in from a fairly wide audience. And so I'm not sure that all this information is spot on with any particular needs, but the point to be made is understanding how to apply the tools to your applications, and then expanding its use based upon the additional knowledge. All right, so it looks like we've got a plurality of contributions here. So we're going to give this another 5 seconds, and I appreciate your participation and attendance. I'm going to close this, and here's how people have weighed in on this topic. And so you've come to the right place to discuss this. All right, so let's jump back into the discussion here. What I want to do today is basically refine some of the terms that we're using and make sure that we're all on the same page as far as the definitions and the significance of the time element in these two applications. As I mentioned, PowerFlow contains the feature impact motor start, and transient motor start is actually a subset of dynamic stability. And both are tools that are based upon PowerFlow, and they just handle time differently. And then we'll jump into some examples. So as I mentioned, the two different ways, or each of these ways, is an approach to looking at a system from basically different standpoints. Flicker can result from motor starts which cause voltage spikes of short duration, and normally these are less than 2 cycles. And so if we're in an area where there's a lot of motor starts and we're concerned about multiple starting motors and their effect on the system, then the impact motor start is a good way to take a glance or a snapshot of what that means in normal operations for our system. Then voltage sags can be longer duration, and this can happen when we start large motors under load, and in some cases significant sags can actually bring down parts of the plant unintentionally. Now, just a real quick reference to the motor starting curve. As we set up a motor in EasyPower in a model, we have described its function and characteristic starting curve that we refer to as the TCC curve. And what we see here is this violet line that looks like a chair. This is the separation between the normal operations of the motor and the abnormal, or what's considered potentially abnormal part of the curve, where we're plotting time versus current. And so in theory, if we apply full voltage to this motor, it can potentially draw as much as, in this case, looks like almost 1,000 amps. And that voltage, or that current draw, can last as long as potentially 3 seconds. Now, so that would be an impact of just slamming that motor onto the system at full load. On the other hand, if we have the motor coming up to speed, so that doesn't, and as I say, let me just kind of get to the next slide rather than amplify it. So the impact motor start solves the PowerFlow equations using the current injection method. That's the methodology that EasyPower uses, which makes it much more efficient in solving PowerFlow for very large systems. The tool establishes a quiescent point where everything is equalized out, and then it applies, for the impact motor start, it applies the kVA constant load from that motor curve with a locked rotor and takes a snapshot of what the system would look like as a result of applying that load. So PowerFlow is a snapshot in time of the voltage and current flow and power flow in the system. And normally when you solve the power flow, you describe what those conditions are. So impact motor start essentially then applies that load, which is described in this particular dialog box. We can open up the dialog box, indicate that we want to start this motor while the rest of the system is at quiescent point, and then we want to start it with a 0 scaling factor, which means we want it to start with 0 rotational speed. So we will do that, and then at that point we look at the equation results, and we can look at the different voltage responses and sensitivity to the voltage that's going to result as far as that current spike. Okay, so let's jump into EasyPower and do this. So we're going to use an example that's in the installation folder under Protection 1. If you go to if you have EasyPower tools, you can go to open one line in the one lines folder. Under samples, you'll find this Protection 1 example. So it's this one right here, Protection 1 DEC. And what I want to do is go into PowerFlow and solve the equations. And what this does is shows us these are the power flow, the real and imaginary power flow in each of the circuits. In this case, because we have this icon here at the top indicating the motor load, this is real and imaginary load for these individual motors. And we're also looking for voltage sensitivity. So we have a threshold set, I think at 0.95 pu, and we see that under normal operations, we're right at that point as far as voltage drop on these remote buses. So the question I have is, what happens if we start this motor under full load while everything else is at this quiescent point? I'm going to double click on this motor icon itself, indicate that I want to start this motor, and we're going to start it at 0%. So this is an individual motor. It's been characterized and set up in the one line diagram. Now again, we've resolved the equations without this motor online. And now as we solve with the motor applied as a constant kVA load under these initial conditions, this is the response, or this is the resulting voltages and currents that we will see. We'll see that this bus drops to a 0.84 per unit. This drops to a 0.922. If I have any sensitivity or any sensitive equipment on these remote buses, I may want to consider, and I have to start this motor fairly frequently, I may want to consider that impact on these other devices. Now what I'm looking at, or what I control, is under my PowerFlow options. My control settings are the under voltage threshold, Well, I might say, well, 0.95 is normal. I've got my stuff hardened to 0.90. What would be affected in this case? And I can see I still have some issues here, that there could be an effect on this main switch gear if any of these other motors are have a problem. Now, so that's impact motor start. And the tool will give us a voltage report of anything that has been flagged, and we can look at what happens to the system with and without that case. Now, if I come back here and go to unflag that, take it back to 100% load. Now, I'm not going to get into all the details of PowerFlow. It's maybe something that you want to do at some time. Different from what we just the step we just went through is the smart breaker feature in EasyPower. As I cycle this breaker, it puts this motor on and off the system. And the tool resolves the PowerFlow equations, and I can see the result of that. And so that's a little different effect than the impact motor start, because we have a resolve of the equations with this kVA in the system rather than a constant load at those impact motor start parameters. Okay, so that's impact motor start. It's a feature in PowerFlow, and it's very useful. And if you want more details, you would basically look for voltage violations. And now, one other point here is, if this is a group motor, if we've defined this motor as a group of motors, let's say 200 horsepower, and I only want to start one of the motors in the system, I might scale this at 50% and start it from that point, and so I can see what the result is of doing a motor start in that mode. So we'd solve and do an impact motor start, and even a partial load start indicates that there's a problem. It's less dramatic, but the tool lets me look at that approach. Okay, so that's PowerFlow and impact motor start. Let's back out of this. Now, as I mentioned, the transient motor start is actually a separate module, and it's a subset of dynamic stability. And what that means is it uses a full flux model for simulation, and the motors are characterized now such that they can respond to the change in the voltage and current of the system as a potential variable load that would respond both to current changes in current and voltage. To enable this, we have to go into the stability tab of the EasyPower model for the motor and bring in these different variables that can be imported from the library as standard, or they can be digitized from a torque speed curve for the specific motor that you have. Then when you go into dynamic stability, that same smart breaker feature will enable it to put it online, and then you'll see the transient response of now changing the status of the system, and consequently the results will reflect the actual system parameters as that motor comes up to speed. So let's jump into EasyPower and show this. This is probably one of the most fun modules we have. All right, so here we have several large motors, and I'm concerned about what the effect is of bringing one of these motors online while the others are there. I can do the same thing as I had with PowerFlow. In fact, just like we did before, if we solve this, everything at quiescence looks pretty good. If I come out and if I want to do a motor impact impact motor start with this. I got to put a 0 there. And so this is showing me the worst case flicker, if you will, worst case spike of bringing this system online, or this motor online, when everything else is running full speed. Now, if I want to take that a step further and I want to actually see the response as the speed of the motor picks up, then I need to use transient motor start or dynamic stability. And if I go back to the database edit, we can see that the icon looks different on the motor parameter, or the motor icon itself. If we go to the stability tab, you can see we have selected from the generic library a standard induction motor, and we pull it in from the library. We can use the power factor and efficiency that we have entered ourselves, or we can override it with whatever's coming out of the library. If we don't override it, then it's going to more accurately approach the parameters that our motor would have. And as I mentioned before, if we wanted to digitize it, the tool would let us do that by overlaying a PDF copy of the speed torque curve and letting us approximate a curve that would produce these variables. Then there's a starting model. In this case, we're using speed squared, and a running model, which we're using speed squared. Once we set up this model now, the icon changes and it looks like a little induction rotor. As we go into stability, it opens a three frame platform. And now I'm going to open and resolve this breaker. So right now we're looking at the quiescent condition that the motor, the PowerFlow equations all converge to. And if I exercise this breaker, then the tool knows that I'm trying to start this motor, and it displays the voltage, the current, the speed, and the torque, the braking horsepower on that motor. So now I still have the spikes that I was talking about, but I also have the realistic voltage and speed draw as described by the flex model for this particular motor. Now, where people find this very useful, especially in the case of these large motors having to start under load, is the ability to tune a soft starter so that the system won't be susceptible to these changes in voltage. For instance, if I wanted to plot MCC3 as this motor starts, I think I've got it under plot 4. Maybe plot 3. I've got MCC. Here's MCC voltage, current, and M4 per unit. So this is the voltage, current over here. So this is the current flow and voltage. So we see a voltage sag while this other motor was coming up to speed, and that could have an impact on the rest of my system. So again, we're looking for the impact of individual operations, and it may be difficult to do a lot of trial and error starts with a soft start programming, whereas if I go back to my EasyPower script, I can actually develop a script in dynamic stability that shows me the effect of certain levels of soft start voltage as the motor comes up to speed over time. Okay, so the bottom line here, and so these are all, there's a lot of other capabilities in PowerFlow as well as dynamic stability, and so all I've just explained is the fact that transient motor start is actually the ability to calculate PowerFlow solutions at every half cycle for as long as I want, with any input changing or any other perturbation in the system that I want to apply or to respond to. whereas impact motor start is strictly just applying a full kVA load, constant kVA load to the system at normal operations and seeing what the worst case result would be. All right, so again, there's a lot more to this, and I'm not going to spend time doing that, but hopefully that kind of addresses what the main question was. What we're able to see then with transient motor start is different voltage, current, speed, fuse melts, breaker trips that would respond or be the result of any particular stimulus in the system. So what have we learned here? PowerFlow basically simulates the worst case across the line transients for an impact motor start of a single motor or group. We can start up to 10 motors at a time, and then look for bus sensitivity as different thresholds can be adjusted and flagged with the controls in PowerFlow. Transient motor start, on the other hand, applies a full flux dynamic simulation and then plots the PowerFlow results at half cycle time steps and allows to look at voltage sags or swells any place else in the system based upon a single point of stimulus or multiple points of stimulus in our in a script. And so that could be, again, that's another feature it's worth getting into details on. And a lot of people that do dynamic simulation of adding alternate energy sources like photovoltaic or wind turbines to an existing system have an interest in those types of simulations. Okay, I think that kind of covers what I want to talk about today. I appreciate you attending. If you've got questions, you're more than welcome to contact me or tech support. And be sure to check on the website. We're starting to schedule out training sessions, regional training for next year. And if you have time or want to also look into the online training, which is now available, you're welcome to do so online or contact your sales support. Thank you very much for attending. Have a good day.